Hello students, and welcome to our lesson on the characteristics of graphs. Essentially, we're going to be talking about where the graph exists, where it's going, and what it's doing in the middle. So basically, we're just describing how a graph looks and the directions that it goes and what is and is not allowed to be in there. So first things first, what is the domain of a function? The domain of a function includes all possible x values for which the function is defined, meaning that there is an output. Okay, so for example, if we define a function as 1 over x, you're not allowed to plug in 0 because 1 over 0 is not defined. But any value for which it is defined is in the domain. To find the domain on a graph, so if we have a visual, we're going to read the graph from left to right, just like you read a book, and the domain will go from the leftmost x value to the rightmost x value, smallest to biggest. The range of a function, okay, the range of a function includes all possible y values for which the function is defined. So now we're talking about the outputs, or how high and low it goes. To find the range on a graph, we're going to read it from bottom to top. The range will go from the lowest y value to the highest y value. And so I'm just going to make a special note that bottom to top is a little bit counterintuitive, hard word to spell, for us, because generally we read top to bottom. But when you read the graph, you want to start with the lowest y value and go to the highest. And the lowest one is, well, it's down low. So we got to read it bottom to top. All right, so now in what ways can we state the domain? This is how we communicate domain and ranges to each other. The domain and range can be stated using sets or intervals. Okay, where depending on the situation, one is better than the other, but generally speaking, intervals are what we use the most. But really, we just use whichever one is more convenient, but you always need to check what a problem says to use, and you need to meet that criteria. So if it says to use an interval, make sure you use an interval. Set notation will normally include an inequality to describe the domain and range, such as x needs to be less than 4. Okay, that's an example of an inequality. Whereas interval notation always uses, well, they're called intervals, but we use brackets or parentheses and we put the smallest and largest numbers on either side. So on the left and right, we either put a bracket or a parenthesis. And on the other side, same thing, bracket or parenthesis. One of those two is going on each side, but not both, of course. Okay, we just pick one. On the right side over there, you can see there's a couple little bullet points. If we want to include values, we use a bracket. And if we want to exclude values, we use a parenthesis. We also graphically will describe this using either a closed dot or an open dot, where a closed dot means to include where that dot is, an open dot means to not include or to exclude where that dot is. All right, so bracket include, parenthesis exclude. On the inside, we have one of two things. We're either going to have negative infinity and infinity if the graphs go forever left, right, up, or down, or we're going to have the small number on the left where notice negative infinity, even though it has infinity in it, that's actually the smallest value possible. So it's either negative infinity or the smallest number. On the other side, it's either positive infinity or the big number. So we always go from smallest to biggest, and if those things go infinitely far, it's negative infinity to infinity. All right, we're going to see a whole bunch of examples right now, so I won't bother explaining too much right here. One other note, though, is that if it is an infinity symbol that you're using, it will always be parentheses because we don't include infinity. Because infinity is not actually a number, it's more of a concept, just to represent that it goes on forever in that direction. All right, so let's see a bunch of different ways we can write this down. If we have all values less than 2 on a number line, this is going to look like starting at 2, okay? And it says all values less than 2, so that means 2 is not included. So I would put an open dot at 2 and all values going off to the left because less than is in the negative direction. So for example, to the left, it might go 1, 0, -1, all the way down. So all values less than 2 are all the values to the left of 2. As a set, we could say that this is the set of all x such that x is less than 2 with an inequality like that. Okay, so this is read as the set of all x. So these squiggly braces diagnose that it's a set, or they can tell you that it's a set. And then it's the set of what? Well, it's the set of all x's. Okay, why all x's? Well, that's the variable we're referring to right now because we're talking about domain, and domain has to do with x's. So it's the set of all x. This vertical line right here means such that. Okay, vertical line means the words such that. So it's the set of all x such that x is less than 2. So over here on the right, we give a description, in this case using an inequality. But generally speaking, we're just going to use an interval to write this. So since it's everything less than 2, that means it can go infinitely far in the negative direction. So on the left, we're going to have negative infinity. And on the right, we're going to have the 2, which is the biggest number we're allowed to be. But since it doesn't include 2, so it doesn't say less than or equal to 2, just less than 2, we're going to use a parenthesis on the right side to say that 2 itself is not included. All right, so now moving forward, I'm going to cheat a little bit and I'm going to put some number lines in place. So bear with me 1 second as I draw a couple of these. And by draw, I mean cut and paste. Work smarter, not harder. That's the trick to math. Mathematicians are inherently lazy. Don't forget that. All right, next one. All values less than or equal to 4. So this is nearly the same as the first one. Less than or equal to 4 means we're going to be going off to the left of 4. That's the less than direction. But I'm going to put a closed dot at 4 because it says or equal to. Okay, so the or equal to tells me to close the dot. Okay, that means that 4 itself is included. Now for the set notation, we can always write that full set notation with the set of all x such that x is less than 2 stuff. But generally speaking, in this case, we would just use the inequality itself. So we can skip the set notation and just go straight to x is less than or equal to 4. Where I have an or equal to part, I have that bar on it for the same reason I have a closed dot. And so as an interval, we're still going all the way to negative infinity. We're going all the way left, but we're going as high as 4, and we are including 4. That or equal to part means that we include 4, so I use a bracket on the 4. Okay, next one, all values greater than 1. So we're going to start at 1, and we're going to go to the right because it says greater than. We're going to use an open dot because there's no equal to. We could say x is greater than 1 as an inequality. And as a set, since 1 is now the smallest number, but it's not included, I'm going to use a parenthesis with the 1 on the left, and we're going to go all the way up to infinity, and because it's an infinity, always a parenthesis. Then we have all values greater than 5 inclusively. Okay, this word inclusively means to include that number. So all values greater than 5 means we're going to start at 5 and go up to the right, but we're going to close the dot because it's inclusive. So let me go ahead and put that dot in blue to make it a little more clear. We're going to close that dot. So this is all x greater than or equal to 5. So I'm going to add the or equal to it. And then because it's including 5, we're going to put a bracket on the 5 and go all the way up to infinity. But again, infinity always gets a parenthesis. Next one, all values exclusively between -4 and 7. So -4 on the left, 7 on the right. Exclusively means that we are not going to include those numbers. We're going to exclude them. So we're going to put open dots on each side, and then we'll go ahead and connect those dots to represent including everything between those numbers. As an inequality, we put -4 on one side, x in the middle, and 7 on the other side. And these are strictly less than symbols because we are not going to include the -4 or the 7. And that is also going to tell me to use parentheses in my interval. -4 is the smallest and 7 is the biggest. All right, last one, all values except -3. So I'm going to put -3 on the graph. I'm going to put an open dot at -3 to represent it is not included, but I'm going to draw arrows in both directions because it's everything except -3. As a set notation, there's 2 convenient ways we can do this. We can either say x is not equal to -3, which means it's everything except -3, Or we can say all real numbers except for -3, where that symbol I wrote in the front, that fancy R, it's two straight lines down and then the R, that means all real numbers, which means everything. And the slash -3 just means to delete -3 from that list. So it's everything except -3. But generally speaking, we use the one above it. X does not equal -3. As an interval, it's actually kind of tedious to write these because you need two intervals. We need -infinity to -3, and we also need -3 to infinity in order to include all of this. And in the middle, we put a union symbol, which looks like a U, but you don't put that line down on the right side. So it's more of like a cup, kind of. All right, that's how we do intervals. Now we're going to be using that a lot moving forward. So first few examples, we want to state the domain and range of these graphs. So to do the domains, we're going to say how far left and right it goes. To do the ranges, we're going to say how far bottom to top it goes. So first one, for the domain, this graph goes from 0 all the way to the right. And notice it's an arrow on the right side, so it goes infinitely far to the right. Notice it's an open dot on the left over here. And so on the left side, we're going to use a parenthesis at x equals 0. And on the right side, we're going to use an infinity because it goes infinitely far up. That's what that arrow on the right side of the graph means. Okay? And we're going to put a parenthesis on that infinity. All right, for the range, we read bottom to top. So we're going to start down here at -1. And we're going to go, again, infinitely far in the other direction because there's an arrow pointing up on the right side. So we start down low at -1, which is not included, and we go all the way up to infinity. Number 2 is a little bit more complicated because it switches directions a couple times. So for the domain, it's not too bad. We start at -1 on the left with a closed dot, and we go all the way to 2 on the right with an open dot. So our domain is just a bracket on -1 to +2 with a parenthesis, because we include the left, but we don't include the right. The range is what's a little bit trickier. Because you use the same y values more than once, you might think that we're not going to include 0 because this open dot on the right side. But because this graph uses that y value in a different spot, we are going to include it. So on the bottom end, we're actually using this -0.63, and on the top end, we're using this +2.1. So our domain's a little bit ugly here, but both of those are included. So we're going to go all the way as low as -0.63 with a bracket, and all the way up to 2.11 also with a bracket. So just be careful that even though we're missing a spot in the middle here, it's filled in by these other two spots that have a y value of 0. So it kind of seems like we're not using 0, but we are using it in other places, so it gets filled in. All right, number 3, from left to right, we have arrows on both sides, so we're actually going infinitely far in both directions. So we're going to go from -infinity to infinity. Another way we can say that is just a fancy R, all real numbers. Okay, so if you don't want to do -infinity to infinity as an interval, the other option is the script R. But again, make sure if it says to use an interval, you have to use the -infinity to infinity. All right, and the range, we're going to go as low as -3, and we're going to go up all the way to infinity because of those arrows. So our range is going to go from -3, which is included, all the way up to infinity with a parenthesis. All right, so now some examples where we don't have a visual, which means we have to take into account the restrictions that are possible. So first one is y equals x. The graph of this function is just a straight line that has no restrictions. You can plug in anything. And so all real numbers is our domain, where you could also say -infinity to infinity. Okay, both of those mean the same thing, both work, no restrictions. Number 5 though, we have 1 divided by x. X here is not allowed to be 0. So if you were to sketch this graph, it has 2 pieces. We'll learn about this function more later, but it has 2 pieces where we do not use in the middle this x value of 0, okay? Because the graph is undefined when we get there. And so we would say that x here is not allowed to be 0 because that denominator is not allowed to be 0. So we can either say that the domain is all real numbers except for 0, or as an interval, it's negative infinity to 0, union 0 to infinity, where we have to write both sides of the interval. So that corresponds to the two branches, is what they're called, of this graph over here, branch 1 and branch 2. Number 6, we have a square root function. A square root function starts at the origin and then goes up and to the right. So we are not allowed to plug in anything on the left side of where it starts. The rule is quite simple, that when you have a square root with an even index, so in this case, square root already implies that it's a 2 as an index, but when you have any root with an even index, the inside here, so the radicand, x has to be greater than or equal to 0. So as a set, x has to be greater than or equal to 0, or as an interval, we can say that this is 0 to infinity, where we include the 0 with a bracket, but infinity always gets a parenthesis. All right, next one is x squared. X squared is nice and easy because it is just a U shape. It's defined for all real numbers. And so this is either fancy R for all real numbers or negative infinity to infinity. Number 8 is an absolute value graph that looks like a V, very similar to x squared, but a V instead of a U shape. That is also defined for everything, so all real numbers or negative infinity to infinity. And the last one is a cube root that also has no restrictions. It looks like a sideways cubic graph, like I drew there. And so again, all real numbers or negative infinity to infinity. So what we should take away from this section is that the two main things we're looking for are division by 0, which is right here, or square roots or radicals that have even roots. Okay, in the future, in other classes, you'll learn about logarithms, which also have restrictions. But for now, it's really just division by 0 and even rooted radicals. All right, so now some easy things. Increasing, decreasing, and constant. We've all presumably seen an escalator or at least a staircase. And so we all know what it means to increase or decrease in elevation. And being constant just means you're not changing. So that's when you're going flat. So real easy here. Increasing intervals are parts of the graph that are going up from left to right. That means that they have a positive slope. Decreasing intervals are parts of the graph that are going down from left to right, meaning they have a negative slope. And then constant intervals are parts of the graph that are flat, which means that they have a slope of 0. Okay, to be flat just means you're not going up or down, so your slope is 0. And like the domain, these intervals are stated using the x values where they begin and end. So graphs can go up, down, or just stay flat. Along with that, if you're going up and down, you might be changing direction at some point in the middle there. So we have what are called turning points. So a turning point is exactly what it sounds like. It occurs where the graph changes direction or changes slope from increasing to decreasing, or the other way around. Turning points are referred to generally as local extrema due to their output values being relatively extreme. So what that means is that if you zoom in enough on a turning point, it will appear to be the highest or lowest point. So for example, it might look like the top point on this little U shape here, or it could look like the low point on a similar shape. So when you think of local extrema or turning points, just think of mountaintops and valleys. It's either the high point or it's the low point. Depending on which one of these two cases you're in, high point or low point, you're either going to be going from positive to negative or negative to positive in terms of slope. So if the graph switches from increasing to decreasing, the point is a local maximum. And that is the first example over here that I drew. So I'll actually move this little doodle over to here. Okay, it goes up and then it goes down. If instead the graph switches from decreasing to increasing, then that point is going to be a local minimum. And so notice that that one goes down and then it goes up. So decreasing to increasing creates a little valley at the bottom. So those are local extrema or turning points. The other kind of points we have are called absolute extrema. And these are the highest or lowest points over the entire domain of the function. So absolute extrema can occur at turning points, which we already talked about. So the top of the turning point might be the absolute extrema. It might be the highest point, but they can also occur at endpoints, which would be the far left or the far right side of the graph if there is any endpoints. Or they can also occur, and this one doesn't have a bullet point, sorry, they can also occur at breaks in the graph. And we're not going to talk about this possibility at all in this lesson, but imagine you have some crazy function where it goes up and down and does this stuff, and then it kind of flattens out. And then imagine on the other side, it starts real low all of a sudden, and then goes up again. So although we don't really have endpoints on that graph, this point down here is lower than all the other points. And so that would be the absolute extrema. That would be the absolute minimum of that graph. But not all functions have absolute extrema. So you'll notice in this little doodle I just did, if I were to just keep going on the left and right side towards the top, then this graph is going to go up infinitely far on the left and on the right. So it's not actually going to have an absolute maximum because these arrows are never going to stop going up. So we just won't have a top point. It goes up for forever. But on the bottom, we would still have this absolute minimum down here where that point is lower than all the other points. All right, so absolute extrema, I would argue, are some of the simpler characteristics because it's just either the highest or the lowest point. There's not too much to it. Whereas turning points, which are local extrema, have a little bit more to their definition because it requires that you actually go up and then down, or vice versa. So you need two things to happen. Whereas absolute extrema, just the highest or the lowest point. All right, next thing is concavity. Concavity refers to how the rate of change of a graph is changing, so how the slope is changing. And we can talk more about that in a rate of change lesson. But for now, we're just going to think of concavity as either being a smile or a frown. So a graph is concave up on an interval if it curves upward like a smile. So if it's curving up, that would be concave up. Looks like a nice happy face. The graph is concave down on an interval if it curves downward like a frown. So if it's getting more and more negative, okay, that's the exact way to describe it. More negative, think frown. And more negative just means that it curves down like that frown. All right, and then if we have a point where it changes concavity, that is an inflection point. Okay, so a point of inflection or an inflection point is where we change concavity from up to down or vice versa. All right, so now we're going to put all that into practice in a nice little picture here. So we want to decide on which intervals the graph is increasing, decreasing, and constant, so going up, down, or neither. And we also want to decide on which intervals the graph is concave up and concave down. And then we'll identify the extrema and inflection points. So we're going to do the easy part first, which is where is this graph going up or down? And so we can pretty clearly see that on the left side, this graph is going down all the way until we get to negative 2.2. And then it's going up after that all the way until we get to x equals 0. Then it's going down again. And then it goes up again. So if we want to describe these intervals, we can say that the graph is increasing in two different spots. It's increasing on the left, which is negative infinity, all the way up to negative 2.2. So I use these x values, this negative 2.2 right here, and then because it goes infinitely far, I use infinity as the other x value. All right, but there's another interval where it's going down. It is also, oh, sorry, I wrote increasing. I meant it is decreasing on this interval. We are going down right here. Let me fix that real quick. So decreasing. Okay, we are decreasing on the two red spots. So from negative infinity to negative 2.2, union positive 2.2 to positive infinity. And notice that I did not use brackets on any of those parts of the interval because at these points down here, these turning points, and this point up here, which is also a turning point, we're not going up or down. So you have to think of turning points as neither increasing or decreasing. They're just nothing. It's the point where you switch. So imagine you go on a hike, you get to the top of the mountain, and then there's a bench up there for you to sit and take pictures. So if you're up here on the top of the mountain, you're not going up or down. You're not hiking at all. You're just standing, taking your picture, or sitting on the bench. You're just resting. So it's neither. So that's why parentheses on both ends. All right, this graph is increasing now in all the other parts. So the parts that I drew green lines next to, which go from negative 2.2 up to 0, and then union from 2.2 to infinity. And you might have noticed I made another mistake in this section. So on that decreasing, I put this one right here, 2.2 to infinity, but that is not correct. That's this green line here. And so this one is here, 2.2 to infinity. So that second increasing or that second decreasing interval needs to change. All right, so a little correction over here. That second decreasing interval is actually this one in the middle of the graph, which is from 0 to 2.2. So we're just going to correct that from 0 to 2.2. Notice now that we have all four intervals are different. We have negative infinity to negative 2.2, negative 2.2 to 0, 0 to positive 2.2, and positive 2.2 to infinity. So if we put those all four together, it makes up the entire graph except for the extrema. Okay, so the only thing left out of those intervals is the turning points, I should say. And so we can go ahead and say that there is a local max and a local min, where the local maximum is the point at the top of the mountain right here. And so that is at x equals 0. And there's two local minimums on either side of the graph. And one is at negative 2.2, the other is at positive 2.2. So x equals negative 2.2 and x equals positive 2.2. And notice that these three values right here fill in the gaps in between these intervals. So if you put those in, these are the turning points that we had left out of the increasing, decreasing intervals. All right, so that's going up, down. Now we got to talk about concavity. So when we look at this, I'm going to use the highlighter. We're going smiley face style all of this left section of the graph till we get to right here. Okay, and then we're going to be frowny facing everything in the middle here. Notice this looks like a frowny face all the way up to that dot. And then we're going to be smiling again for the rest of this graph all the way up to infinity. So we can go ahead and categorize these intervals. Okay, we are concave up on two intervals. One of them is from negative infinity all the way to this point right here, which is negative 1.3. So negative infinity to negative 1.3. And then also from positive 1.3 to infinity, okay, which is the right side of the graph. And then we are concave down on the interval in the middle, which is from negative 1.3 to positive 1.3. All right, and then we can make a note that there are two inflection points. So inflection points are those two dots where we switch. So one of them is at x equals negative 1.3, and the other is at x equals positive 1.3. And this graph happens to be symmetric, by the way, where these values are the same, just negatives of each other. That's not always the case. I just chose a graph that was symmetric for the example. But so we were able to label all the extrema, which are these 3 points. Oops, I circled the wrong one. All the extrema are these 3 points here, and still circled the wrong one. Gosh, I'm all over the place in this one. The extrema are the maximum here, the minimum here and the minimum here. And then the inflection points are the 2 points where we change concavity, which are these 2 spots here. All right, now let's go ahead and talk about positive and negative intervals. So a positive interval is the part of the graph where it is above the x-axis, meaning the y value is positive. And a negative interval is the parts of the graph that are below the x-axis, meaning negative y values. These intervals are separated by the x-intercepts of the graph, which are the places where the graph touches the x-axis. So all we have to do is check, are we above or below the x-axis over here? So for each of these intervals, we're going to label them as positive or negative, and then we're going to identify the x-intercepts of the graph. So we have a bunch of intervals here. Let me zoom out just a bit. So first interval is negative infinity to negative 3. So if we're looking just right here, negative infinity to negative 3 is just this part of the graph. This part of the graph is below the x-axis, so we would say that this is a negative part of the graph. Then the next interval is negative 3 to negative 0.65. That's right here on the graph. This is above the x-axis, so we would say it's positive. The next interval is from negative 0.65 to 3, which is still above the x-axis, so that's also positive. Then we're going to go below the x-axis, 3 to 4.65. So this is going to be negative. The next one, 4.65 to 6, also negative, below the x-axis. And then 6 to infinity is the part on the far right over here. That is going to be positive above the x-axis. So now the intercepts are where we change from negative to positive or vice versa. And really, they're just where we touch the x-axis. So we can also have x-intercepts without changing sign, but it's wherever we touch the x-axis. So this spot here, here, and here are all going to be x-intercepts. So we have x-intercepts at negative 3, positive 3, and positive 6. For number 12, we have 3 intervals. We have the interval on the left that's below the graph, below the x-axis. This is the negative interval. And then the rest of the graph is all positive. Everything afterwards stays above the x-axis. Our only x-intercept is this point right here where we touch the x-axis, and that is at negative 3. So now one other quick example. We could also have a graph that touches the x-axis but doesn't turn around or doesn't cross through it. So imagine we just have a basic parabola, looks something like this. So this graph would be positive the whole time, but right here, we would still have an x-intercept at x equals 0. And so that would still be an x-intercept even though we did not cross through the x-axis. So all you have to do is touch it to be an intercept. You don't have to cross it. All right, last thing we're going to talk about is end behavior. And end behavior comes up quite a bit because it's how we describe what happens over the long term for functions. So the end behaviors of a function are used to describe where the y values of the graph are headed as you approach the left and right ends of the graph. So we want to know what is the far left doing and what is the far right doing. We don't actually care what's happening in the middle here though when we talk about end behavior. We just care far left and far right. And we have some notation that allows us to say this easily. So as we follow this graph to the left, the y values go down. So if we look at the left arrow here, it is pointed down, okay? The way we write that is as x goes to negative infinity. So that means as we go left, what does the y value do? It goes down. And so we say that the y value goes to negative infinity. So as x goes left, y goes down. Okay? On the right side of the graph, so this arrow over here, this is going up and to the right. So we can say that as we follow this graph to the right, the y values go up. And the mathematical notation is that as x approaches infinity, that arrow means approaches. As x approaches infinity, y approaches also positive infinity. So as we look to the right side of this graph, the graph goes up. Okay, as x goes left or right, so negative infinity or positive infinity are left and right, y goes either up or down to positive infinity or negative infinity. So a couple examples with this. Numbers 11 through 13. For 11, we have as x approaches negative infinity, y approaches, and this is also, or this is going to be positive infinity. The left side of this graph is going up. The right side of this graph is going down. So for our other answer, as x approaches positive infinity, y approaches negative infinity. It goes down. For the number 12, both sides of this graph are going down. So we would say as x approaches negative infinity, the left side approaches negative infinity because we're going down. The right side, as x approaches positive infinity, is also approaching negative infinity because, again, we're going down on both sides. We don't always have to approach infinities, though. We can also approach a constant or a number. So for number 13, on the left side, this graph is going up, but on the right side, it's flattening out. So we can describe that as x approaches negative infinity, y approaches positive infinity. The left side goes up. But on the right side, as x approaches positive infinity, y approaches -2. It approaches an actual number, not infinitely far up or down. So we don't always have to approach infinity or negative infinity. We can also flatten out to any number. All right, so now putting this all together, we just want to find out which of these are true for the graph that's shown below. Part A says f of -7 equals 20. Well, if we look at this graph, it seems like it's referring to this point over here, which has 20 and -7. But that point actually says that f of 20 equals -7, which is the opposite of what part A is saying. So we're going to say A is wrong. Part B says f of x is increasing from negative infinity to infinity. This graph is always going up, right? It's always going in an upward direction, and it's presumably going to keep going. So this is true. It is always increasing. C says the y-intercept is 0, -12. Y-intercept is the spot where it crosses the y-axis. And so we can look and see right here, 0, -12 is the y-intercept. So that's good. That one works. As x approaches negative infinity, f of x approaches infinity. That one is wrong because it says the left side goes up. But right here, we can see the left side is going down. And so that one is incorrect. E says f of x is negative from negative infinity to infinity. That looks like it might be right. But if we think about it, this graph is going up. And it has an arrow pointing up. So it's going to keep going, and eventually it's going to cross this x-axis. So it's negative on the part we can see, but eventually it's going to cross and become positive. And the last one says f of 8 equals -10. That middle point on the graph does in fact say that f of 8 equals -10. The input of 8 corresponds to an output of -10. And so that one is true. And that is the end of this video. Hopefully you enjoyed learning about the characteristics of graphs.